Okay, so I think we should start now since we have so many presentations to look at. So hello everyone, my name is Paulo Rauber and I'll be the host for the event today. So first of all, welcome to the EECS Research Week webinar for the Game AI group. So let me first explain to you how this event is organized. So first of all, Professor Simon Lucas, who is the head of the Game AI group, will say a few words about the past, the present, and the future of our group. After that, we'll have 10 quick presentations where different members of our group will talk about their work. So during these quick presentations, we will not have time for questions, but you can already send the questions during the presentations using the Q&A features or the chat. So after all the presentations are done, we'll finally, hopefully we'll have time to answer all of your questions. So without further ado, Simon, would you like to introduce our group?
Yeah, fantastic. Okay, as Paolo said, I'm going to give a quick overview of the group's past, present and future. So we believe that games provide a perfect testbed and application domain for AI, and they're also fun. And that's sort of our founding principle, to make the most of these observations. So we founded the group in 2017 when a bunch of us moved from University of Essex to Queen Mary. Since then, we've grown really significantly, and we now have 10 academic staff and more than 25 PhD students and postdocs. We play a really active role in the research community, and we organised and hosted the first IEEE conference on games in 2019, and that was a great success, held here at Queen Mary with more than 400 delegates. We've got really good links with the games and tech industries, and our main focus is to study cutting-edge game AI and to apply it to really interesting problems. We're also a really sociable group, and we have games night most weeks. So on the background of the slide, you can see a visualization of random rollouts, and also in this image here. And the reason I've put that there is that they're the basis for many of our statistical forward planning algorithms that we use really extensively in the group to achieve a kind of general game AI. And typical algorithms include Monte Carlo tree search and rolling horizon evolution. And these are kind of the overall high-level algorithms, and obviously there's many variations on these, and quite a lot of interest and devil in the detail. So having AI that can quickly adapt to play a wide range of games paves the way for really interesting game design tools, and also automated game design and content creation. So the AI that we use can rapidly test and evaluate novel games and game content. And our group is also known for a good deal of work in this area, including systems like Angelina, Dinesh, and Weather. So these SFP methods work well across a wide range of games, but not all of them. For example, Rolling Horizon Evolution, it's human competitive on Planet Wars, this simple but nice RTS game here, and yet it struggles on Pandemic. So we feel as though in many ways we're just scratching the surface of what's possible. Lots of great research to be done and amazing possibilities to improve on real-world decision making. And we also do lots of fun games like this one down here is Tribes. So lots of things to be done in this space. So one way for people to join us is via EECS. So that's our EPSRC Centre for Doctoral Training. This takes on at least 12 fully funded PhD students each year, so 6 at Queen Mary and 6 at York. And we have more than 100 partners from the games industry and tech industries, and also indie developers and university research groups. It's a 4-year program and includes training in games design and games programming, as well as research methods. Each student does a placement in one of our partners, and we currently have more than 70 PhD students across the program. So you join a really sort of large and vibrant cohort. So IGI covers pretty much anything that's sort of technical and to do with games. It includes game AI, of course, games with a purpose, also to do with things like gamification, computational creativity, and game experience and design. So if you're interested in applying, the link is just there. So that's a bit about the past and the present. For the future, we plan to grow further and become even more successful, strengthen our engagement across a range of sectors, including industry partners, other research groups at universities, and also government. We feel that game and game AI have a great role to play in making our country be governed more efficiently, let's say. So lots of scope for real world decision making. We run an interesting set of seminars, and these will carry on into the future. And we're also setting up a Turing interest group on game AI. So watch out for seminars to do with this as well. And we also like developing general game frameworks in order to study these ideas in very systematic and kind of sound ways. And these include at the moment Gridley, Stratiga, TAG, which is tabletop games, and XKG, which is cross-platform games in Kotlin. So please find out more about us in the web link there. And also you can follow us on Twitter. So that's it from me for the moment, but I'll come back and give a talk later in this session. But for now, I'll hand over to Mike Cook, who's going to be our first technical speaker. So Mike, over to you.
Sorry, of course, my internet blipped at that exact moment. Let me share my screen. All right.
Yeah, it works.
Fantastic. Hey everyone, my name is Mike Cook. I'm a research fellow here in the Game AI group. And today I want to tell you just a little bit about my work in automated game design. So I've been building automated game designers for the best part of a decade now. They're little AI systems that design games on their own. So sometimes those games look like these little abstract arcade games on the left. Sometimes they're weird platformers about the news, like this one on the right. And making computers design games is interesting because you have to do a lot of things that AI are perhaps not very well suited to. And the thing with this is that when you're probably familiar, with a lot of ways in which you've tried to get AI to play games in the past. So when we get AI to play a game like Go, for instance, that humans already play, we can give it lots of extra information about how experts play, what strategies are good, maybe even past like recordings that humans have played in the past. And that really gives the AI a step up. And even when we're trying to do general game playing, like this is DeepMind's attempt to get computers to play Atari, we still give the AI lots of advice and help that get it on the way. So even the fact that we're using Atari games, these are games designed by humans, they're classics, thousands, tens of thousands of people have played these games. So this is a real advantage for an AI trying to learn them. But when we try to get AI to design games on their own, we're often stuck giving them games that they've invented, no one else has seen before. It could break every rule we know about games. And also the game probably doesn't work. And that's really hard to detect. Just by looking at this game, we have no idea what it's about or how to play it. So one of the techniques that we've come up with at Queen Mary that can kind of help an AI understand a game that it's never seen before and doesn't know anything about is called reversibility analysis. And I just wanted to give you a little flavor of what that means today. So let's say we've got this game that's about pushing a crate around a space to get to a goal. And we want this computer that we've got to come up with this game. We want it to understand something about the moves in this game and which ones are more significant and worth looking at. So for instance, if we just move our player around, this kind of action is very easily reversed. We can press just one more button to undo that action. So we move right and then we move left again. And we call these actions immediately reversible. And these actions are not very interesting. They're very easy to undo. They don't commit us to anything. If we were to move this crate by pushing it, this action is reversible, but it's a little bit harder to reverse. So we have to walk all the way around to the other side of the crate. We have to push it back again and walk back to where we began. So this move is reversible, but it takes a lot more actions. So we call these eventually reversible actions, and they're a little bit more interesting. And the longer the chain of actions required to reverse it, the more interesting the action tends to be. And finally, what about this case where we push the box into a line of other boxes? And in this case, we actually can't get around to push the box back. This move can't be reversed. We call these actions irreversible actions. And these are normally very significant. They're very important to the rule set. And they tell us something important about what this game's about. So by using this kind of reversibility analysis, we can take a game that we know nothing about and gain a little understanding about the texture of its design and decision space. If you want to see more about this kind of work, we wrote a paper about some of the algorithms that this enables. And if you're interested in automated game design or questions like this, you can find out more at my website, possibilityspace.org, or say hi on Twitter. I'm at MTRC. Thanks.
Thank you, Mike. Our next speaker is Nathan.
Aha, I was muted before I shared my screen. Excellent. Hello. I am Nathan. I am a PhD student here at Queen Mary, and I investigate using machine learning to do testing and debugging game AI with neuroevolution. So, I was working on a game a while back, and it was a sports game, and it used some cool techniques to drive the behavior of the AI agents. It used influence maps and utility functions, and some steering to get some really cool behavior like this. Apart from that is not core behavior, that is the AI running into a wall, which immediately begs the question, why is this happening? But that means it's time to debug, and I had to debug influence maps, which that is one of 7 for that particular AI, and utility functions. And those graphs each represent one of the functions that is happening every frame. That is a lot of data to dig through to figure out why it's running into a wall. Oh no. The problem here is that the tools to aid and methods to aid developers reasoning about their game AIs aren't actually that great at the moment. The sophisticated game AI systems, they've got a lot of situations to deal with. The more complicated the game, the more flexible they have to be, and the more things they have to sensibly deal with. And all of those need testing. If a bug does appear, because there's so many situations and eventualities, it can be quite hard to actually reproduce that bug, even if you know it exists. And at the moment, that's all human labor. The automated testing systems just can't be flexible enough to really investigate all of these situations. So enter neuroevolution, which is the love child between genetic algorithms and neural networks, and my pet favorite style of machine learning. It evolves a population of neural networks using a fitness function, which is just evaluating a game state and then figuring out how good that is, which is entirely subjective. It's been used to play games. This is a video of MARIO, which is using a neuroevolved agent to play through Super Mario World on the SNES. The question is, what if our fitness function, instead of trying to play a game well, was trying to find bugs within the system? So my work uses evolved adversarial agents playing against the human authored game AI. And as they play, the fitness function is encouraging exploration of behavior rather than specific victory. By exploring behavior, you can look for erroneous behavior within the human authored agent. The speciation of the neuroevolution algorithm that I'm using encourages searching a wide range of behavior, so all of the various weird situations that might happen will hopefully be covered. And I'm currently investigating if replays from adversarial agents cause different perceptions of bugginess in a human authored agent compared to watching human players playing against it. Thanks a bunch.
Thank you, Nathan. Now we have Simon Colton.
Hello there. Okay, so I'm Simon Colton, and I'm just going to put this on full screen. I'm a professor in the group, and I'm going to talk today about casual creators. So these are apps where having fun meets being creative. So if you've ever made a piece of music on your mobile phone, or you have drawn a picture on a tablet, then you've probably used a casual creator. Now we make these in the group so we can study them properly. And our research questions revolve around how to make them the most fun possible and how to make them as empowering as possible. This is the first one that we made a few years ago called Weather, and it's available on the App Store, iOS App Store if you're interested. And with this, you can make full-on mini games with many levels, literally in minutes. And the design patterns for this involve, first of all, making things easy for the users. So we boiled down game design to making a few choices by tapping and dragging things on a screen only. The second design characterization is to reduce frustration. So it's quite frustrating between making a game and playing a game and having to get your heads in both spaces. So we really made an instant transition between game design and gameplay. It's very, very fluid. And finally, a good design practice is to steal great ideas from other people. So we looked around and we realized that people like playing bouncy physics-based games with emojis. So we made that the subject of this app. The second app we made was called Art Done Quick, and this will be released very soon. With it, you can make decorative imagery like the pictures you see here. And making things easy here involved making sure that it's instantly generating nothing which is ugly or uninteresting. So pictures which are at least a good starting point. And that was not easy. It probably took me about a decade to get that right. Reducing frustration involves not having to wait around. With evolutionary art, which is what this is, you often have to wait long times in order to see something of interest. And finally, we looked at other apps and we realized that people love doing things like drawing and liquefying images. So we put them in as post-process editing tools. The final app that I'm going to talk about is called Style Done Quick. And this is brand new. You are literally the first people in the world, other than me and my wife, to see this app. It will be released hopefully this year. With it, you can do fancy image filtering called neural style transfer, which is very good at what it does, surprisingly so. And here, to make things easy, it's not all that easy to blend and layer stylized images. You need something as powerful as Photoshop. Casual creators don't normally do this, so we've imported that. To reduce frustration, we decided not to have any in-cloud processing. So normally, images are sent off to the cloud, are processed with a deep learned neural network, and then they're sent back. That's very slow, and you have to have a network connection. So everything is now on device. And finally, if you look at the user interface design, it's called neomorphic user interface design, which is a cool new thing. And that was a great idea we stole to make this look good. Okay, so if you're interested in casual creatives, do check out the work in our research group, and also that of Kate Compton. She has a PhD thesis on this. She's co-organized workshops at the International Conference on Computational Creativity, and her website, galaxykate.com, is full of interesting stuff. Please do follow me on Twitter if you're interested in this, Simon G. Colton. And there's a website coming at artdonequick.com. Thanks very much for listening.
Thanks, Simon. Our next speaker would be Vanessa, but Vanessa couldn't join us today. So instead, Nathan is going to share a video that Vanessa prepared for us.
I have too many windows, bear with me.
Hello, I am Vanessa Volz, and I work at Model AI, a startup company that is building AI solutions for the games industry. I am also an honorary lecturer here at Queen Mary University. Today, I want to talk to you about evaluating game levels with the help of AI techniques. Why AI techniques? Well, imagine you're a game designer and you need to pick one of these 3 Mario levels to go into your game. The problem is, these levels are all very different. The leftmost needs you to identify and remember the specifics of the level so it doesn't fool you. The middle one needs you to execute difficult techniques flawlessly. And in the right one, you get to just sit back and enjoy the music. All of these are levels designed in Mario Makers, so with the exact same tool. And they certainly have similarities, but also lots of differences. I really wouldn't know which one to pick. So maybe instead, what we could do is to find levels that a lot of people enjoy, and then just pick levels that are the most similar to that type of level. But then figuring out similarity can also be very difficult. Take these 2 games as an example. They are 2 different mobile games by the same company, and they play pretty much the same. You build your base and produce resources. But visually they look different and they are marketed differently. One is a casual game and one is strategy. And they seem to reach different amounts and also types of people probably. The question now is, maybe an AI technique could pick up on similarities that are in the game, in the data, and not be fooled by visuals and marketing. So in some recent publications, game levels have been represented as continuous vectors. Which vector is represents which level is decided by our neural network. It is trained in an adversarial process. There is one network that generates levels from vectors, and one network that decides whether the level is similar to the levels it has already seen before. As you can see in this video, similar vectors represent similar levels, and changing a vector just by a little bit usually results in only small changes in the level, at least visually. So maybe we should just pick the level with the shortest distance in vector space? Not quite. More work is definitely needed to also ensure that the level plays similarly, not just looks like the same level. So we are going to continue working on this. Follow me on Twitter if you're interested in hearing more about our progress.
Thank you for sharing, Nathan. Our next speaker is Ivan.
Hi, everybody. I am a PhD student in the group, and I'm gonna do this brief presentation. It's called "You Better Behave," and it's about improving automated play testing using AI. So imagine you have a new game that you just designed, and you want to understand how it could be played. You may have some insights on it, but of course you're extremely biased, and so you want to give somebody this game to play test so that they will tell you how it plays or how it could be played. Unfortunately, using humans is kind of hard because it takes a lot of time, resources, and of course humans are themselves biased. So how can we do that? We can do that using artificial intelligence. And so the idea is that you can decide sort of the space of behaviors by defining some metrics. And you could end up having a variety of different behaviors in your game, which could be, let's say, a paladin or a melee player, and so on and so forth. And so this means that the AI needs to be extremely flexible to represent all these behaviors and even more. But also it needs to go beyond the game itself, because you want to produce something that is applied to many different levels. Otherwise, the AI is used just for a single game, and that is not optimal. And so the idea is to have different metrics that can describe this behavioral space. And usually you have an artificial general intelligence that plays a game, and it uses a score described or defined within the game to play the game. So to decide the actions that it wants to take. And this AI has a bunch of parameters, and by changing them, you will hopefully have different behaviors. Our approach instead is having an AI that processes logs of events. So basically, this log represents the dynamics. So what happens in the game as the AI plays. This log is then processed using an event value function, and it produces an artificial score. And the idea is that this will add parameters to the AI and will have a much broader opportunity to represent different behaviors. So this is a simple example where using score signal, you basically don't get a really wide set of behaviors, whilst using event logs, you can have a much broader representation of these behaviors. These experiments were run using a game that is called Splendor, implemented in my Rinascimento framework. The idea is that event logging can be easily automated. It's a general method, and it allows to have fast search. And this is an example in even a wider set of behaviors or more precise behaviors. This is using score, and this is using events. And so it is clear how this method can represent a wider set of behaviors. Thank you very much. If you're interested, you can search for these papers and myself on Twitter, or contact me by email. Thank you very much.
Thank you, Ivan. Our next speaker is Raluca.
I am muted. Hi. So I am Raluca, and I am also a PhD student in the Game AI group, and I'm going to talk a little bit about modern tabletop games. With this term, we mean any sort of analog game that can be played on a physical surface, such as board games, card games, or role-playing games. And modern here refers to those games that are of high complexity. They contain many different types of game pieces, many rules and types of interactions between many players. A lot of these games also hide part of the information available to the players, such as part of the board or some players' hands. And players often take on different roles within the game, and each game has a series of parameters that control its flow and balance. These games may include both cooperative and competitive aspects between players or between the players and the game, and they often have many actions that the players need to consider at a point in time. All of these features make them very interesting problems for diverse artificial intelligence methods. To this end, several of us from the Game AI group, as well as some external partners, have been working on a tabletop games AI framework that we call TAG. TAG simplifies the digitalization process of these types of games, providing much of the core needed to implement a new game. All games are developed so that both humans and artificial players can easily interact with them. And we include readily available AI players that can be plugged into any of the games. The framework includes other useful tools, such as game analysis reports, data logging, game and AI players, improvement tools, and graphical user interfaces that can be used from the prototype stage of a new game to be later customized for full user interaction. We currently have 8 games implemented and several more in progress, with several competitive artificial players as well. Tabletop games generally present so many exciting opportunities of research. Go play one and think how an AI method would do something that is happening in that game. To study these applications of AI in these games, we've put together the TAG project, which is all about building a collection of tabletop games and AI players able to play them all. Do check it all out yourself, download the GitHub repository, have a play, and maybe even start implementing your favorite game today. If you'd like to read more about the project, we have 2 papers available that go deeper into the details of the framework and all the technical details and more of our motivation behind it. Thank you for listening.
Thank you, Raluca. Now it's my turn. So hello everyone. Once again, my name is Paulo Rauber and I'm a lecturer here in the Game AI group. So I work in reinforcement learning, and reinforcement learning is the study of agents that interact with an environment by observing states and taking actions that ideally maximize expected cumulative reward signals. So why reinforcement learning? If you believe, like I do, that intelligence measures the ability of an agent to achieve goals in a wide range of environments, then reinforcement learning is an ideal framework, is an excellent framework to study some fundamental challenges that any intelligent agent will face. So some of these fundamental challenges include things like planning, which is challenging due to its computational cost and unreliability, other imperfect models of the environment. Exploration, which is challenging due to the lack of approaches that are both scalable and principled, and representation learning, which is especially challenging in partially observable environments, despite recent advances in deep learning. Now, while thinking about these fundamental challenges, I occasionally solve some much simpler but still interesting problems, and recurrent neurolinear posterior sampling, which I'll talk about today, is one of these problems. Or should I say it's one of the solutions to these problems. So suppose that you're tasked with recommending products to different clients, and each product has an associated profit or reward if your recommendation is accepted, but there's also an unknown probability of this recommendation being accepted. And suppose that your goal is to maximize the expected cumulative profit after giving a finite number of recommendations to different clients. This problem is analogous to the problem of choosing between slot machines, which are also called one-armed bandits, with unknown payoff probabilities. For this reason, this problem is considered a multi-armed bandit problem. Naturally, you'd have in this problem to balance between exploration, which corresponds to recommending each product sufficiently often to estimate its popularity, and exploitation, which corresponds to recommending the most profitable product so far. So if a feature vector provides a context for each decision, such as information about a client, then this problem would be considered a contextual multi-R embedded problem. However, the success of a recommendation may depend on information about the time and the results of previous recommendations as well. And in general, a context vector may have to encode the entire history of interactions between the users and the recommendation systems to enable good decisions. So in our work, in this specific work, we propose an approach that is based on a recurrent neural network that receives the raw history of interactions between the users and the recommendation system and predicts the reward for a given recommendation for a given context. So this eliminates the difficult task of handcrafting an appropriate historical context for decision-making. And in order to balance exploration and exploitation in this approach, we employ a technique called posterior sampling. So if this all sounds interesting to you, the paper can be found on Archive, and you can also visit my website to learn more about my work. So thanks for listening, and I believe the next speaker is Álvaro.
Hi, I'm Álvaro, and I'm going to be talking about some of the research I've been doing during my PhD. The setting we're going to consider is also similar to Pablo, where an agent interacts with the environment and learns a model of the world. And within this context, I'm going to be discussing two ideas very briefly. The first is how an agent can correct its own predictions of what is likely to happen. And the second is how can it learn to assign certain value to an observation from its own perspective. To contextualize the first idea, imagine the game of Mini Pac-Man. Here, the agent has certain expectations regarding its presence in the task or the number of ghosts that should appear. So in other words, the prediction must satisfy some constraints. But for example, if we look at these two simulated sequences of future events, in the first one, we can see that Mini Pac-Man has been duplicated. And in the other one, Mini Pac-Man suddenly disappears. So on the long term, these errors tend to accumulate, making these simulations unreliable as they start to diverge greatly from what can possibly happen. To try to fix some of these issues, we propose this architecture where the agent generates multiple hypothetical futures, but also instead of just using them to get a combined prediction, they can be used to extract information to produce a corrected version of the frame, or at least a more consistent one. Now, the other thing that I want to briefly talk about is regarding utilities or reward functions. Here, the main idea is to try to translate certain principles from physical and biological systems into the language of information dynamics and information flows, and to try to avoid the more prevalent notion of utility as something predefined externally by a researcher. In the research, we work with this additional channel of communication that corresponds to internal variables of the system in analogy to those in biological organisms, such as blood pressure and temperature and so on. The agent estimates a density over these signals, which is also updated in time. And although initially all the signals do not convey any meaning, the agent learns to act in order to preserve certain statistics, which then lead to a circular and self-reinforcing dynamics, as it's shown in the video. So thank you.
Thank you, Álvaro. Our next speaker is Diego.
Hello, everyone. My name is Diego Pérez Liebana. I'm a senior lecturer in the group, and I'm presenting today General Strategy Games Framework. It is implemented in the context of a project in which other members of the group, like in the slide, Alexander, Jorge, Dominic, and Ethan, are also working on. So we do AI for strategy games. And why strategy games? Well, they are very complex environments. In a way, they approximate somehow many real-world situations. And they are very complex for decision-making in AI. Essentially, they bring together aspects like passive observability, not being able to see the whole game state or the whole world state. They have multiple factions trying to compete for a common objective. They have multiple units that each unit of this faction needs to be coordinating. And it also needs to make decisions at multiple layers. For instance, a strategy game could be deciding at an economy level, a research level, units level as well, and some other aspects like, for instance, diplomacy. Now, current AI methods struggle to provide a good performance, good playing behavior for these particular games. In the games industry, for instance, many handcrafted scripts or basically rule-based systems that are programmed into the games are normally quite weak. Some other AI methods that are normally trainable, that require some previous training in the games, suffer from a lack of flexibility and adaptability to be able to play and react to unseen situations. And the statistical forward planning methods, which are ones that we are quite interested in this project, require a forward model. They are good because they can make actions or plan action decisions in real time. However, they do require to have this forward model that needs to be available, be fast, and be reliable. A forward model is essentially an entity that allows you to roll the state forward. Given a current game state and an action that you're applying to it, you get a new game state, and that allows you to do planning. However, in games, the games themselves are the forward model. However, games actually have states that are very large and they're very slow to move forward. So the idea of the project is, can we automatically simplify these models? Can we simplify this game state representation to have a minimal expression? Now, can this expression could be lighter, could be faster? Could the SFP method still be able to plan with them? Now, we're going to try these ideas with a new framework called Stratega. Stratega is a general strategy game framework that allows you to implement multiple games via YAML files, allow you to take logs of the games and analyze the results. But most importantly, they allow you to specify different game states and be able to specify how these models can be extracted. We will propose a new competition on strategy games. Normally in these competitions, we have an AI agent that is going to be playing one game or a set of games, that's the traditional way they are implemented. However, we're implementing a new competition in which what we do is to provide a fixed agent, which allows you to focus only on these abstraction models. So the participant will have to understand how to simplify models that already exist in the game and how to focus on the important parts of complex environments. This is all in a project which is called Abstract Forward Model for Modern Games. It's an EPCSRC funded project for 30 months, in which we are a bunch of people from the QML team, and we're also working with the games industry, with some research companies in the UK and also the UK government. Thank you very much.
Thank you, Diego. Our final presentation is by Simon Lucas.
Mute. Thanks, Paolo. It's amazing how quickly they all went, actually. I think everyone's keeping the time, so I'll try and also keep the time. So I'm going to talk about hierarchical statistical forward planning, and it goes on really nicely from the talk that Diego just gave, actually. So these are the group members that I've been working with on the slide. So let's see what this is about. So SFP methods, I really think they're incredible, and I think the world hasn't fully woken up to just how amazing they are. So on the right of this slide, you'll see 3 different games. One's Asteroids, one's Planet Wars, so Asteroids single-player arcade game, Planet Wars 2-player RTS game, and then at the bottom is Cave Swim, which is like a gravity-based one-touch casual game. So they're 3 very different games, and they're all played to kind of human competitive level by the exact same rolling horizon evolution algorithm that works by evolving random rollouts to make them better. And you can see the evolution process unfolding in real time on these slides. And they are really, really amazing. So it gives you instantly adaptive behavior across a wide range of games. However, they're not perfect, and these methods can also fail if the reward landscape is too flat. So you're not seeing any reward within your horizon. So if you look at a typical kind of travel example, if I want to travel from London to Edinburgh, I don't start off by planning how I'm going to take every single step. I first of all think in high level terms, am I going to get the train or the plane? So that's the main concept. This has been looked at in the AI community for decades, the overall problem of hierarchical planning and learning. We were inspired actually by a recent 2019 IDGCAI paper on sub-Go based temporal abstraction in MCTS, pictured on the right here. And the nice thing about that is if you think about trying to define general macro actions that make sense across a range of different games, well, it's really, really hard. However, if you just define a sub-goal predicate, that is, you take a state in the state space and you just decide, is it a sub-goal or not? That's actually quite a lot easier. And that's what they did in the EECS paper, where they decided that in the grid world example, the doorways would be sub-goals. So for the agent, which is the X was in a doorway, that would be a sub-goal. And in Tetris, if a Tetronimo lands in the wall, that's also a sub-goal. However, they were hand designed. So that hand design makes them less general. So we did a re-implementation of this and started developing our own algorithms. And this is a version you can see running where we have the sub-goals in the doorways, just like the EECS paper. And the magenta lines, these are the kind of macro actions that connect these sub-goals. So you take a macro action by going to a sub-goal from wherever you are at the moment. So we had the idea that what about if you could just pick the sub-goals to be any random point in the search space, and all of a sudden we can make this very general. And so this is a whole bunch of work that we're doing on this. And there's a web page here which is on that link. So we start off with 0 sub-goals. So this is a simple grid world, but we think the methods are very general. And it basically doesn't work. So the agent's trying to find the triangle in the top right. It gets no reward until it gets there. And you can see that with a random sub-goal, so with the doorway sub-goals, it works. So what about now? I'm going to make some at random and restart it. And hopefully it's going to work. So what it's doing now, it's doing these rollouts to the sub-goals. And each time it does a sub-goal, it's also going to make random rollouts from the sub-goal. And you can see that it's a game changer. So instead of failing to find the goal at all now, it finds it every time. So we're quite excited by these techniques. So please follow the link to find out more. And by the way, this is running live in the web browser. You can play with it yourself, and that's done with our XKG framework. So that's it for my talk. I just want to mention for the EECS, we've had some interest on that in the questions. I understand the EECS website, yeah, like really unfortunately is down at the moment, but there are other places where you can find out about this.
It's back up.
Oh, it's back up. Okay. Okay, even better, it's back up. I just want to mention that the deadline for applications for this year is January the 31st. So you've got a couple of months in which to work out your application.